Good afternoon. I am Chanda Devnath. I am pursuing my PhD from Mysore, Badhampur in organic synthesis. So I am working as a TA. I am working as a TA for Professor Nandita Madhavan. So for the course of Mechanism in Organic Chemistry. In the last few classes, I have discussed some basics reaction mechanisms like substitution, elimination, and try to discuss their reaction coordinates with the energy potential energy diagram. So here in this class, I have tried to discuss some theory which supports our concepts about a reaction, organic reaction, and it will also help us to determine reaction mechanism for a unknown reaction. So in the last class I discussed about E1CV, then electrophilic aromatic substitution, then I discussed about potential energy diagram, how we will draw the potential energy diagram for endo and exothermic reaction. Then I discussed about what is activation energy and how we can calculate that, and in presence of catalyst how the activation energy gets reduced and the reaction get catalyzed. So in this class I will discuss about Hammond postulate and Hammet principle. So first we will discuss about Hammond postulate. So for my first instance, some people get confused about these two postulates because they are a bit conceptual, but when it is clear to you, it will be very easy to solve any questions you are given. So what Hammond told, he said that for an exothermic reaction, so in the last class I have discussed how the energy profile diagram for exothermic reaction and endothermic reaction will be. In that I have shown that for endothermic reaction, the energy of the reactant is always lower than the energy of the product. That's why it absorbs energy to get that activation state and form our product. And in case of exothermic reaction, the energy of the reactant is always less than that of the product. That's why it needs less amount of energy, and that excess amount of energy which is reactant has than that of the product. See, this is the product energy, this is the reactant energy. So this amount of energy reactant has greater than that of the product, and that amount of energy gets released. That's why it is a exothermic reaction or exergonic reaction. So now Hammond told that in case of exothermic reaction, the transition state is, you know what is transition state? When the substrate goes to the product, the state where the bond breaking or bond making take place, that is called transition state. That is a very transient and it is not isolable. That's why it's called transition state. So in case of exothermic reaction, this transition state is closer to the energy of the reactant. Transition state is closer to the energy of the reactant. So this is the reactant energy and this is the product energy. Now in case of this exothermic reaction, this is for exo. This is for exo. How will know? Whenever the substrate energy is greater than that of the product, energy of the substrate is greater than that of the energy of the product, then that is exothermic. Now in this type of reaction, the transition state is closer to the energy of the reactant. See, if you can see very easily that this is the product energy and this is the substrate. So the transition state is closer to the reactant energy. The transition state is closer to the reactant energy. And as it is closer to the reactant energy, it has some resemblance with that reactant than that of the product. And in case of endothermic reaction, the reverse happens, because in case of endothermic reaction, our energy of the substrate is always less than the energy of the product. That's why it gains energy from the system to take part in a reaction. And that's why in this case, in case of endothermic reaction, the transition state always resembles with the product, because it is closer to the product energy. This is closer to the product energy. That's why the transition state has greater tendency to look like, or the greater tendency to behave like that of the product. And what is the effect of these features on the reaction? Whenever the transition state resembles more than that of the product, in that case, product stability has a have a huge effect on the reaction, because in this case the transition state is closer to the product energy. So the transition state resembles with the product. So if the product stability somewhat presents in case of transition state also. So if the product is stable, transition state will be stabilized. Suppose if, as it has some product nature, so if this product gets stabilized, this will also get stabilized, because it has that type of nature in it. Okay, that's why whenever a transition state resembles with the product stability has a huge effect on the reaction. And if the transition state resembles with the substrate reactivity has huge effect on the reaction. Okay. If you get confused about this topic, please stop me and ask about that. It's a very easy, but you have to you have to understand all the lines. Now you can see, as I said, in case of this is which type of reaction is this, endo or exo? As the substrate energy is lesser than that of the product, so that's why it is endo. Now in this type of reaction, as I said, the transition state has some product nature, because transition state energy is closer to the product and resembles like product. So as much as product gets stabilized, the transition state also gets stabilized. And this transition state shifts somewhat in the left hand side. That's why the transition state somewhat try to behave like, or somewhat try to looks like the substrate. Okay, so what is thing, whenever, let's say it's getting closer to the substrate, the transition state is getting closer to the substrate, which reduces the activation energy, See, here in this case, the transition state in this A is greater than that of this C. So to perform a reaction through this pathway will be easier than that of this A pathway, because in this A pathway you need greater amount of activation energy. You have to give more energy to the reaction. But in case of pathway C, you have to give less amount of energy. That's why in case of endothermic reaction, as much as the transition state gets stabilized or product gets stabilized, the activation energy gets reduced, and the transition state resembles with the substrate. Now let's discuss our very known reaction, that is SN1, from the aspect of Hammond postulate. We know this type of reaction, this is simple SN1 type of reaction, because reactions came first, the postulate came after that. So we have to prove that our postulate is applicable for all the type of reaction, or it will help us to, if we explain a known reaction by this postulate, then we can easily explain any unknown reaction if we get. So let's see, this is the SN1 reaction, our very known, where first the leaving group will leave from the system. This is the slow step. After that, the nucleophile will enter to the carbocation and generate our desired product. This is the energy profile diagram where the reactant goes through a transition state. What will be the transition state? Here will be the transition state will be like kind of this way, where the carbon chlorine bond gets with delta positive. Okay, and it forms this intermediate I. Then after that the nucleophile attacks, and what will be the again the nucleophile. So here which minus delta negative. Delta means there is a pseudo positive character. It's not as fully electron deficient, but it is partially electron deficient. That's why it have a delta positive and it's partially electron deficient, delta negative, and give us our desired product. Now if we apply our Hammond postulate in this case, you can see Hammond, we can consider the first step, that is the rate determining step of our, this is the rate determining step of our reaction. This is first step. This is the rate determining step of our reaction. This is endothermic in nature. This is endothermic in nature. And we know what will be the endothermic energy profile diagram, where the substrate will be lower than that of the product. Now Hammond, as we have discussed earlier also, in case of endothermic reaction, as much as transition state gets reduced, the activation energy this shifts towards the sub-reactant, and the activation energy we need, that is also get reduced. Therefore Hammond postulate suggests that the activation energy of the rate determining first step will be inversely proportional to the to the stability of the carbocation intermediate. So the carbocation intermediate gets more stabilized, the activation energy gets reduced. The carbocation stability increases, activation energy decreases. If carbocation stability increases, the energy will decrease and activation energy also decrease. Carbocation, so here you can see the tertiary carbocation is highly stable. So in that case, we need less amount of activation energy. After that, we have secondary carbocation, that we need somewhat bit more than that of the tertiary, and in case of primary carbocation for SN1 reaction, we need the highest activation energy. Okay, I think it's clear. So in this type of SN1 reaction, as we know earlier when we discussed about SN1 reaction, what we told that in case of SN1 reaction, the 3-degree carbocation always react faster than that of the primary carbocation. From the Hammond postulate also that we can prove that the 3-degree carbocation, that is the tertiary carbocation, the activation energy less, so that's why it will react faster. Okay, the activation energy is less, and this is the rate determining step. This is not the rate determining step. Here the primary has the less activation energy than that of the tertiary, but this is not the RDS. That is this is not the rate determining step. So the reaction is not controlled by this part. Reaction is controlled by this part only. So if you just consider this one as a RDS, then your concept will be totally reverse, because in that case this will be the less amount of activation energy, so it should react faster. Okay, I think it's clear. So 3 degree halides will be more reactive than that of 2 degree and 1 degree counterparts in reaction that follow SN1 mechanism, and this also matches with the experiment of the SN1. So in first case we discussed, this is the SN1 reaction, and Hammond postulate successfully describes and support our result whatever we got from the simple SN1 reaction. Now second concept we will discuss, that is electrophilic addition. Before going to the discussing electrophilic addition from the aspect of Hammond, I will just first introduce what is electrophilic addition, because I haven't discussed it earlier maybe. So what is electrophilic addition? An electrophilic addition reaction is a reaction in which the substrate is initially attacked by a electrophile and overall result a addition of one or more relatively simple molecules across the multiple bonds. So what is they saying? For initially attacked by electrophile. So first the double bond will react with the electrophile and generate a carbocation intermediate. So this is our alkene, where this will take this double bond will take this proton and a carbocation center will get generated, and after that a nucleophile will come and form our desired product. In this case, the first step is the slow step. The first step is the slow step. So this is the energy profile diagram where the substrate slow step, and this is also endothermic. Also endothermic. So this is our first step where the activation energy we need delta E1 star to form this intermediate. After that it get attacked by a nucleophile from our desired product. So this is our first step where it will take up the proton and form this carbocation intermediate, and after that now there are so next we want to describe whatever result we get from addition reaction from Hammond postulate. So as we have said already that in case of addition reaction also the first step where the taking up the proton by the double bond is an endothermic reaction. The first step is an endothermic reaction. Now the Hammond postulate suggests that the activation energy of the rate determining first step will be inversely proportional to the stability of the carbocation, as in case of SN1. So this is, if you consider this after the first step, this is kind of like SN1. In case of SN1, the leaving group leaves from the system and form the carbocation. Here the double bond traps a electrophile and form a carbocation. So after the first step, the rest part is simply like SN1. So the result will be similar to the SN1. So in case of SN1, the first step is endothermic, and as much as the in transition state the product gets carbocation gets stabilized, the transition state gets stabilized and it shifts towards the reactant. So it has some reactant nature in itself. Okay. So from the aspect of wherever so Hammond postulate suggests that in case of addition reaction, Hammond postulate supports our concept of addition. In case of addition reaction, we always prefers. Now if we consider that in this case the proton can be trapped from this part carbon or this carbon. So if it was trapped by this carbon, what should be the carbocation? this is 1 degree. But in this case the carbocation is 2 degree. The 2 degree carbocation is always stable. So as we said, as much as the carbocation stability increases, that is, it goes to the primary to secondary, the activation energy we require also less. That's why that path will always favorable. The path where we get a secondary carbocation, that path will always favorable over than that of the path where we get a 1 degree carbocation. That's why in this case, when the double bond traps a electrophile, it always go through the carbon where it generates a greater degree of carbocation. Okay, so the Hammond postulate here also correlates with our reaction result. So in case of SN1, the tertiary will react faster. That can be also explained by Hammond postulate as the energy gets reduced. And in this case also, similar to the SN1 reaction, the 3 degree will react faster because of the Hammond postulate that the 3 degree needs less activation energy. So based on that, I have given one question. Just try to solve this one. What they asked, used Hammond postulate to determine which alkene in each pair would be expected to form a carbocation faster in an electrophilic addition reaction. So among these pairs, which one of these pairs will react faster in case of addition reaction? As we said that wherever the higher degree carbocation gets formed, that path will be always favorable over than that of the other. So among this pair, you will always go for that double bond where after addition of the electrophile you will get a higher degree of carbocation. So just try. I will just give 5 seconds. Okay, I hope you guys have decoded it because it's very easy. So let's start. In this case, I will just draw the most preferable pathway. Like the double bond can trap the proton from both of the sides, but where the highest degree of carbocation will form, that path will be always favorable. So I will take that one also only. So if it gets protonated from this side, then generating carbocation is here. Whereas in this case, this is 2 degree, this is 3 degree. So which double bond will react faster? Obviously this one. Among these two, if it is get protonated from this side, the carbocation will generate at this place. If it goes from this side, the carbocation will generate from this place. So it will be 3 degree. And in this case, both the sides are equivalent. So carbocation will generate from this side, carbocation will generate from this portion. It will be 2 degree. So which will favorable? The first one. Similarly, in this case, if it goes from this side, 2 degree carbocation. If it goes from this side, 3 degree carbocation. Okay. So which one will prefer? Obviously this one. So it's clear now. In case of addition reaction, always prefer that one which will give higher valency of carbocation, because the highly stable carbocation needs less amount of activation energy to take part in a reaction. Now we can use this Hammond postulate to explain radical reactions also. So if we see a radical reaction and if we take an alkane and perform chlorination and bromination, we can get two types of product. First is tertiary halide, second is primary halide. How primary halide will form? If proton is taken up from this position, then it will form a primary halide. If proton is taken up from this position, it will form a tertiary halide. Now you can see that in case of chlorination, the selectivity is not that much high than that of the bromination. In case of chlorination, as we know, the tertiary radical is stable, but still we get a very less deviation in number, where the tertiary radical we got, or tertiary halide product we got in 54% and primary one we got in 46%. Rather than in case of bromination, the selectivity is too much high and we got the brominated product in 95% in for 3-degree radical and 5% in for primary radical. How can we explain this from Hammond postulate? How can we explain this? Because chlorination and bromination, both of the reaction going through a same reaction mechanism. There is no variation in reaction mechanism. So what is the factor that is controlling the selectivity of the reaction? That is only can be explained by the Hammond postulate. So if we look into the reaction nature, the first hydrogen abstraction, where after the homolytic cleavage will form radical. Whereas in this case, if we see this form this primary radical. Now for chlorination, the first step, that is this propagation step, this is the where this alkyl radical forms. In case of chlorination, this step is exothermic in nature, whereas in case of bromination, this step is endothermic in nature. So how it will affect this reaction? So in case of chlorination, the first step is exothermic, and as we know the nature of exothermic reaction, the reactant energy will always lower than that of the product. the reactant energy will be in case of exothermic reaction, the reactant energy will always higher than that of the product. So this is the exothermic reaction where the reactant energy is higher than that of the product. And in case of bromination, the first step is endothermic, so the reactant energy is lesser than that of the product. Now, in case of exothermic reaction, from Hammond postulate we have learned that the transition state resembles with the substrate mode. So the transition state resembles with the alkane and the chlorine atom, whereas it has very little radical character, because here the product means the intermediate. You have to know that here the in case of like kind of SN1, here if we just consider this part only, this part of the energy profile diagram, and we are just considering this as a product, but it is actually the intermediate. It is actually the intermediate. For this part, this is the product. For this part of the reaction, this is our product. For this first part of the reaction, this is our product. But if we look into the overall reaction, this is our intermediate, because we are not getting this one as our isolating this one, but if in medium, if there is any anion, that will attack and give us our product. So now, therefore, this transition state has very little amount of radical character, and the regioselectivity is only slightly influenced by the radical stability. As this has not any product character or any radical character, the radical stability does not have any effect on our transition state. That's why the radical stability does not affect much on the transition state. Therefore, the selectivity is not that much high in case of chlorination reaction. We all know that the 3 degree radical is always stable than that of the 1 degree radical. But in case of chlorination, as the reaction is exothermic, the transition state does not resemble with our product, that is our radical intermediate here. Here the radical intermediate is our product. Here the radical intermediate is considering for this part of the reaction, this is our product. So as the radical intermediate stability has no such effect on this one, that's why it has very radical character, and its stability will not have that much effect on the transition state. Therefore, it will not choose the more stable radical or less stable it will not choose the less stable radical. It's not like that. The selectivity will be almost 50-50. But in case of bromination reaction, as the first step is endothermic, the transition state has a large radical character in it, because it's closer to the intermediate energy. It's closer to the product energy, or here it is the intermediate energy. Therefore, it has a huge radical character in it. Therefore, the radical stability always affects on the transition state of the reaction. This concept of the Hammond diagram I have discussed earlier slides also. Just try to correlate. It will make your understanding easier, because if you see every question differently, then it's very, at the end of the day, it is very difficult for you to remember all the concepts differently. But if you know how to correlate each of the problem, then just remembering one concept, you can answer any question arrive in front of you. Unknown, known, any question you can attend. So here you can see, as the radical nature is greater in case of transition state, the radical stability has a huge effect on this reaction. Therefore, the 3 degree radical, as it is more stable, react very faster than that of the 1 degree radical and give 95% of the brominated product and 5% of the first 1 degree brominated product. Okay, I hope it's clear now. It's very simple. Just try to correlate everything. So by the concept of Hammond postulate, we have discussed SN1 reaction, addition reaction and radical reaction. So all the concept we can explain with Hammond postulate. Whatever we have the understanding in case of reaction, that which substrate will react faster, which intermediate will be more stable, which reaction will be Yes, Preeti has raised hand, I think. Okay, so therefore, in that case, we can explain by this postulate, we can explain different type of reaction mechanism. Now let's solve a question. According to Hammond postulate, for endergenic reaction, or endergenic means whichever reaction absorb energy. Endergenic means whichever reaction absorb energy, that can be heat or any kind of energy. So if it is absorbing heat only, that is called endothermic reaction. Endergenic means it is absorbing energy, that can be in form of heat, light or anything. So in general way we are just saying it endergenic. So this type of endergenic reaction state, they have given 4 options. The transition state resembles the product of the step. The transition state is the rate determining state because it has high EA. The step is rate determining because it has smallest EA, and the transition state resembles the reactants of the step. So what they are saying, in case of endergenic, so first try to draw the reaction, the energy profile diagram for endergenic reaction. First, because you know that it is easy, first draw that. For endergenic reaction, the reactant energy will be lower than that of the product energy. Just draw it. Now what they asked, the transition state resembles the product of the step. Yes, of course, as we have discussed, in case of endothermic reaction, this transition state is closer to the product energy. That's why it will resembles with the product energy. Let's see the other options also. The step is the rate determining because it has high EA. Yes, that is also true because it has high activation energy. If it is instead of exothermic reaction, if the next step is exothermic, then that of it has highest activation energy, so it is always the rate determining step. Then so if 2 is correct, then automatically 3 is not correct, and the transition is the reactant. If 1 is correct, 4 is automatically not correct. So the correct answer will be 1 and 2, as it has highest activation energy and it also resembles with the product. It has resembles with the product. Okay. So in case of endergenic or endothermic reaction, the reactant energy is lower, product energy is higher, and the transition state is always resemble with the product. Okay, let's solve the next question. Using this postulate, draw the transition state of the following reaction, which is endothermic. So as it is endothermic, first try to draw the activation, the energy profile diagram. Endothermic, so it will be product. Endothermic means the transition state will be closer to the product energy. The transition state will be closer to the product energy. As our product here is PHCH2 dot, so the transition state will have some radical character. So the transition state will be so this will be our transition state. So this will be our transition state, and it will have more in product character because this is endothermic reaction. Okay. Let's solve our next question. So using Hammond postulate, explain the following reaction. So according to Hammond postulate, in case of addition reaction, that process always favorable where the higher degree carbocation forms, as the higher degree carbocation has less amount of energy, and as much as the carbocation energy is less, it needs less amount of activation energy to go to the transition state. So here, how can we explain? So it will take proton from this H plus. So it can take proton from this pathway or this pathway. So if we take proton at this part, so in this case, the radical will be at this position. This is 1 degree. Whereas in this case, carbocation will be at this position, that is 3 degree. So which path will be favorable? Obviously the 3 degree path, so this will favorable, this will not. And after the addition, we will get this one as our product. We will get this one as our product. Okay, so this will not go through this pathway because according to Hammond postulate, the reaction which goes through a higher degree carbocation, that is 3 degree carbocation, that pathway is always favorable because of requirement of less activation energy. So based on this concept, one question came in NET 2019. So they have asked, according to Hammond postulate, which of the statement is correct. So you have to analyze and find which of the statement is correct. So first one, let's see. The transition state of endothermic reaction resembles with the starting material. That is wrong, as we know. For endothermic, it resembles with the product. For transition state for exothermic reaction resembles with the product. This is also wrong. The transition state of endothermic reaction resembles with the product. This is right, because we know, because from the diagram as we have drawn multiple times. transition state is closer to the product, that's why it resembles with the product in case of endothermic reaction. So let's see fourth option also. The transition state of the endothermic reaction as well as exothermic reaction does not bear any resemblance with the starting material, and that is also actually basically wrong. So the correct option will be option 3. Okay, it was very easy question. So in grade NET this type of question came, and if you know the concept, it is very easy to answer for you, because see, from this you can understand this. Just 2-3 concepts are there, and by these 2-3 concepts you can answer all the different type of questions. Let's talk about our next principle to understand reaction mechanism, that is Hammet principle. So to determine the nature of an intermediate involving in a reaction, Hammet performed a different type of reaction. Hammet performed a reaction of deprotonation with different type of benzoic acid, different type of substituted benzoic acid, like normal benzoic acid, a benzoic acid with electron donating group like methoxy, para-methoxy benzoic acid or para-nitrobenzoic acid. So he performed deprotonation of this reaction by using a base or water and check the reaction constant for the reaction, for this reaction. So when he performed a reaction with simple benzoic acid, he got the reaction constant Kh. Now he performed a reaction with para-nitrobenzoic acid, and in that case he got a reaction constant of Kn2, and so surprisingly, not surprisingly, from his observation, he found that when the reaction was performed in case of para-nitrobenzoic acid, the rate of deprotonation is faster than that of simple benzoic acid, and in case of para-methoxy benzoic acid, the rate of deprotonation is slower than that of simple benzoic acid. So based on these outcomes, Hammet said that Hammond gave a equation where this is log Kx by Kh. Kx means different type of, X means different type of substituent on this benzoic acid. So log Kx by Kh is equal to sigma x. Sigma x is called the substituent constant. Sigma x is called the substituent substituent constant or substituent parameter. Now from whatever value he got in with different type of benzoic acid, he found that when electron withdrawing group is present on the benzoic acid, when electron withdrawing group present in the benzoic acid, when electron withdrawing group, when X equal to electron withdrawing group, in that case the reaction rate is faster than that of benzoic acid, and when electron X equal to any electron donating group, the reaction rate is lower than that of simple benzoic acid. And from this equation you can see, if Kx greater than Kh, so this will be greater than 1, so it will be greater than 1, so this will be greater than 0, sigma x will be greater than 0. And if Kx is less than Kh, this will be greater than, it will be less than 1, and that's why the sigma x will be less than 0 or negative. So if from the, here I have provided some values also to show you that how this value matches with this concept. When this is NH2 group, NH2 group is the electron donating group. NH2 group is the electron donating group. It will donate electron towards the ring. It will donate electron towards the ring. In that case, the sigma x should be less than 0. Here you can see the sigma x less than 0. When it is OMe, that is the electron donating group, that is also negative. CH3 is also electron donating group because of its plus I effect. This is also negative. When it is hydrogen, 0. This that means no effect. And if it's fluorine, it's a minus I effect, positive, I, positive. See, when you go to NO2, it's highly positive. This is highly positive. So, from this you can see that whenever, so from this one you can get an idea that by determining the sigma value, we can get an idea about the intermediate involving in a reaction. So, if suppose you took a reaction and you got sigma positive value, then from that you can get an idea that the intermediate involved in that reaction that resembles with this type of benzoic acid reaction. Okay, so whatever intermediate and whatever transition state is going through, that resembles with this benzoic acid because the value resembles with this one. So if we add, here I have given another concept also, that if the substituent is at the meta position instead of para, the effect is less. See, the effect is different than that of para position. So when the substituent is at the para position, the effect is greater and prominent. Now, Hammet performed all these previous reactions just for benzoic acid, different type of substituted benzoic acid. Now, if we want to apply this Hammet equation for an unknown reaction, which is not the reaction mechanism which is not known. So in that case, suppose a given reaction A to B or A in equilibrium with B. So the basic equation so Hammet postulated, that is log K by K0, or it is also like Kx. So log Kx by Kh equal to sigma rho. Log Kx by Kh equal to sigma rho, where sigma is the log Kx by Kh, the rate constant of the substituted reaction and the simple reaction. Okay, so this is the equation. So here the rho value, sigma, you know, sigma is this one. Sigma I have discussed. Sigma is the log of rate constant of the substituted benzoic acid divided by simple benzoic acid. Whereas this rho known as reaction parameter constant, and it also tells us how sensitive the reaction is to substituent effect in comparison to the ionization of benzoic acid. So it will give, in case of benzoic acid, whatever value you will get, for a different reaction you will get a different value, but this rho value will correlate with that of benzoic acid value. So from that you can get an idea that in our reaction which intermediate is getting involved. Suppose a reaction which has giving a rho value which is similar to that of benzoic acid, that will react or going through a similar kind of reaction pathway. So this equation is also known as a linear free energy relation. Why it is called linear free energy relation? So if we elaborate this equation, you can see how this concept has been already discussed by ma'am. I'm giving a recap. So if we go into the equation, you can see the sigma x equal to the log of rate constant of substituted benzoic acid divided by log normal benzoic acid. Now, as log Kx by Kh equal to log Kx minus log Kh, then after that this rho and similar to this, then from the thermodynamics you know that del G equals to minus RT ln K. Del G equals to minus RT ln K or 2.303 RT log K. So from here, if we just reverse it, then log K equals to minus del G divided by 2.303 RT. So now we apply these values at this position of log Kx value, and just after eliminating just normally mathematical performance, we will get this one. This is the free, so the difference in free energy of the reactant for any reaction is equal to the difference in free energy of the benzoic acid multiplied by the rho. That is, here the free energy of a reaction, an unknown reaction, is correlating with the free energy difference of a benzoic acid through the value of rho. Okay. So whatever value we got in case of benzoic acid, if we multiply with the amount of rho value, we can get our free energy difference of our desired reaction. Okay. So now what is the application? Suppose, as we said, we will take a different type of reaction other than benzoic acid deprotonation. Here we took a reaction which is ester hydrolysis. So here we took a ethyl benzoate ester, and we perform the hydrolysis of the reaction. So this is the reaction pathway where the OH minus will attack to this carbonyl and open up, and then further then OAT minus will remove from the system, and then deprotonation. So from here to here, the reaction is similar to that of the benzoic acid, as the product whatever we got is similar to that of the deprotonation of the benzoic acid. The product is same than what we got in case of deprotonation of the benzoic acid. So we can correlate this reaction with the benzoic acid reaction and get the value of the sigma or the rho value, and from that we can get an idea that how the reaction is getting affected by the substituent, or which substituent will speed up the reaction and which substituent will slower the reaction. That we can get an idea from this Hammet principle. Now he performed a different type of reaction with this substrate with different substituent. When we use different electron withdrawing group in presence of X, in case of electron, when they use different type of electron withdrawing group, enhancement in rate was observed. That is, in that case, Kx is greater than that of the KH, which is similar to that of the benzoic acid. And here, when any electron donating group is given, they got a lower rho value, which shows that Kx is lower than that of the KH. Now if we see the value, in case of simple benzoic acid, the rho value is greater than 0, but is not less greater than 1. The effect is not that much prominent. But in case of different other type of reaction, you can see the value is quite high, and you can correlate them with the gradient, that is rho. So here you can see that we can correlate the reaction of this ester hydrolysis with benzoic acid deprotonation and get an idea that in this case also, if we add electron withdrawing group, the reaction rate will get faster, and if we add in electron donating group, reaction rate will go slower. How this? If we go, this is the mathematical concept. If we look into the electronic concept, what is the reason for that? If suppose this is our intermediate or product, suppose there is a NO2 group, that is the electron donating group. It has a huge minus R effect that will shift the electron density towards it, and that will attract this electron density on this substrate, therefore on this product. Therefore this intermediate gets stabilized. Due to presence of this NO2 group, this intermediate gets stabilized, and as much as our intermediate gets stabilized, from that Hammond postulate, what we have to learn, that as much the intermediate gets stabilized, the activation energy required for that transition state also gets reduced. So you just have to correlate Hammond postulate, after that Hammet. So if as much as the intermediate gets stabilized, the activation energy required for that reaction gets reduced. So the reaction rate gets faster. So this gets stabilized. So the EA for this reaction get reduced. So rate enhances. Okay, I think it's clear. I have tried to simplify as much as possible so that you can correlate all the concepts. So from Hammond we got an idea that as much as intermediate gets stabilized, the activation energy gets reduced, so the reaction rate gets higher. Now from Hammet you can get an idea that which substituent can affect our reaction. So from that you can get an idea, as here the electron withdrawing is stabilizing our substrate. That's why that means our substrate has a huge electron density in our product has a huge electron density in itself, or our intermediate has a huge electron density in itself. When we are adding an electron withdrawing group, it pulling the electron density to itself. That's why our product is getting stabilized and activation energy gets reduced. Now suppose if you are adding an electron donating group which will donate the electron. Now as our intermediate or product was already electron efficient, it has a huge electron density in it. Now you are adding an electron donating group which is donating electron towards that. So the stability will decrease. And as the stability will decrease, the activation energy will increase. From the Hammond diagram you can see, as much as the stability will, we took just simple reaction, the stability will increase, the stability will decrease, the activation energy will increase. As much as the stability will decrease, then the energy will increase, so the activation energy also enhance. Okay, so from there you can get an idea that, so what is the role of Hammet equation? From Hammet equation you can get an idea which type of intermediate is getting involved in our reaction. So from this value or from this diagram you can get an idea that in our reaction a negative, that is a carbon ion intermediate or this type of benzoic intermediate is getting involved in the reaction. Okay. Now let's see some other applications. So if we take this benzoic acid deprotonation reaction for some other reactions like this phenol deprotonation reaction. In that case also the rho value is positive. Rho value is positive means rho, here you can see when from this diagram you can see here the rho value is positive. So whenever the rho value is positive means the reaction rate is higher than that of the simple substitution. That is when there is no substitution. When the rho value is higher, that means the reaction rate is greater than that of the simple substitution. Now in this case, now consider this one. Here you can see there is a minus H plus. So you can consider this similar to that of deprotonation reaction. This is also a deprotonation type of reaction. Now in this case, if we add a substituent, can we explain by this one? If we in this case, if we add a substituent here, then it, and for this reaction, what is our transition state? Our one proton will get removed from the system and we will get this as our product. Now if X equal to an electron withdrawing group, what will happen? It will pull electron towards itself. It will pull electron towards itself. So that's why here the product is this one. Now this has a electron density itself. So if it's pull electron to itself, it can donate electron. So electron gets moved towards the ring and gets stability. That's why here the product gets stability. Okay. In case of benzoic acid, how we are getting the stability? We are getting the stability by the delocalizing the negative charge of the benzoate anion. But here we are getting the stability by delocalizing the lone pair density from the nitrogen atom. So if the X equal to Na2, then it will stabilize the product, or if we say in a different way, if X equal to Na2, it is already has a positive charge. If it move the electron density from the ring, there will be a partial positive character at this carbon. So there will be huge interaction at this position. There will be huge electron deficiency at this position. Therefore, whenever there is electron withdrawing group, the substrate energy get higher. The substrate gets destabilized. And in case of product, the substrate get stabilized. So if we draw this energy profile diagram, it will be similar to that of benzoic acid. If it, this is for H. Now as OMe is given, OMe stabilizes our substrate. OMe stabilizes our substrate. Whereas if it is NO2, our substrate energy the activation energy to go to this transition state get reduced. The activation energy needs to go to this transition state get reduced. Okay. So from Hammett principle, you can explain other reaction also rather than the benzoic acid deprotonation. So in this case, so now suppose in whatever case I have discussed till now, in every case the product or the intermediate we got, that is electron efficient, or there is a electron density in our product or the intermediate. Now suppose a reaction where we are getting a product where there is a electron scarcity in it. So if you add any electron withdrawing group, what will happen? It will be reverse than that of the electron it will be reverse than that of carbon ion intermediate, whatever we are getting in this case, because here if we are adding any electron withdrawing group, it will destabilize our product, and if we are adding any electron donating group at this position, it will stabilize our product. Understood, right? If it is NO2, then it will pull the electron to itself, so there will be a positive charge at this position, so it will be destabilized. And if it is electron donating, then this electron density will somehow get reduced, electron scarcity will somehow get reduced. So that's why in this case the product stability is higher than that of the reactant. The product stability is higher than that of the reactant. So the effect of substituent is reversed than that of the other case. So here, when we are adding electron donating group, when we are adding electron, so if that according to the diagram, this part is for this. So for whenever it is electron donating withdrawing group for this positive reaction, so this will be decreasing, the slope will be decreasing. Because the rho value will be negative, just reverse than that of the other. In other cases, rho value will be positive because in our product there is electron density and electron withdrawing group will stabilize that, so it is similar to the benzoic acid. When it is similar to the benzoic acid, then that will be positive. When it is similar to the benzoic acid, that will be positive. And when it is reverse of the benzoic acid, reverse than that of the benzoic acid deprotonation reaction which was first performed by the Hammett, then it will be negative. Okay. So here I have, if you see these two lines, it has summarized whatever I have told till now. So here a positive rho value means more what is this saying? A positive rho value means more electrons in the transition state and in the rather than the starting material. So what I am saying again and again, that if the rho value is positive, then the product has a huge electron density which can be stabilized by electron withdrawing group. That is similar to the benzoate anion. Your product is similar to the benzoate anion, that is it has a electron density itself, and if the rho value is negative, it will be reverse than that of the benzoate anion, so that your product has a positive character and it has a electron scarcity than that of your substrate. So it has a electron scarcity than that of your substrate. Okay, so if rho value is positive, then your product or the intermediate has a electron density or electron efficiency than that of your substrate. If that rho value is negative, then your product has electron scarcity than that of your substrate. Okay, understood? So from this one, if your rho value is positive, you can understand that a reaction is going through a carbon ion intermediate or any anionic intermediate. The reaction is going through any anionic intermediate, or the product which you are getting is somehow is not a positive, is not a electron deficient product. You are getting an electron efficient product. And if the rho value is negative, but you can get an idea that the reaction is going through a carbocation intermediate or a positive or electron deficient intermediate, and from the starting material has some electron efficiency than that of our product or intermediate. So what is the significance of rho? We are almost at the end. So what is the significance of the rho? So if rho is greater than 1, that is positive, the reaction is more sensitive to the substituent than that of the benzoic acid, because in case of benzoic acid you have seen the values are all greater than 0. When it is electron withdrawing group, values are all greater than 0 but not greater than 1. It's less than 1 because it's point. But in case of other reaction, we have seen the similar type of reaction which is similar to the benzoic acid, correlates with the benzoic acid. In that case, the rho value is highly positive. The rho value is highly positive or greater than 1. So whenever the rho value is greater than 1, the reaction is more sensitive to the substituent rather than the benzoic acid, and negative charge is built during the reaction, which I was telling that in this reaction whenever rho value is positive, in the reaction the product or intermediate you are getting that is negatively charged or electron efficient. And if the rho value is less than 1 and greater than 0, then the reaction is less sensitive to the substituent than benzoic acid and negative charge is built. If it is greater than 0, greater than 0 means it's getting affected, its electron withdrawing group is stabilizing, so it has a negative charge. But it's less than 1, that means it's nearby in the nature of benzoic acid. When it is greater than 0 but less than 1, when it is greater than 0 but less than 1, that means it has similar type of nature along with the benzoic acid. Now if the rho value is 0, then no sensitivity to the substituent and no charge is built. If the rho value is 0, then that means the substituent has no effect on your intermediate or product. That means the reaction is going somehow where there is no charge is generated in your intermediate or your product. So that's why in that case there is no effect of substituent. If I can't remember this type of reaction, if I can get an example of this type of reaction, I will introduce in the next slide, next class. Because in such type of reaction is very difficult where there is no role of substituent. Now, and then the fourth one is where the rho value is less than 0, that is rho value is negative. That means the reaction builds a positive charge, which is the last example I showed, that is this carbocation. Okay, so this summarizes our significance of rho or Hammett equation, where 4 cases can be occur where the rho value is greater than 1, that is similar kind of nature of benzoic acid. Whatever benzoic acid deprotonation is showing, it will show the same but in a greater extent. If it is greater than 0 but less than 1, it will show similar type of effect than like the benzoic acid. If it is equal to 0, then it has no effect. If it is less than 0, then it will be totally reverse effect like that of the benzoic acid deprotonation. That is, the reaction is going through a positively charged intermediate or transition state. Now based on that, we have 2-3 questions to solve. After that, we are over for today. So this question came in some 2019 gate, I guess. This question came in 2019 gate based on Hammett equation. So what they asked that what is the true statement regarding the following reaction. So what they perform, this is a kind of substitution reaction where this gets removed and you can see this is a benzylic carbocation. From both sides this is a benzylic carbocation. So how the reaction will go through, and the nucleophile is not negatively charged. That nucleophile is not that much strong. The reaction will go through obviously SN1. The reaction will go through obviously SN1. So first it will eliminate the leaving group and form a carbocation intermediate. So whenever a carbocation intermediate form, as we have discussed, if the reaction is going through a carbocation intermediate, the rho value will be negative. If the carbocation reaction is going through a carbocation intermediate, the rho value will be negative. So it will be SN1. So these two are already cancelled. So reaction first and third option are already cancelled. So right will be between these two. Now let's see, has a large positive rho value, has a large negative rho value. Which will be the correct answer? This one, because obviously in case of SN1 reaction, while this positive character is generated as the intermediate, the rho value is always negative. The rho value is always negative. Okay, I hope it's easy now. If you have any doubt, you can ask me. You just go through the, I will give the slides and upload the video. If you have any doubt regarding the question, you can ask me in the next class. So let's talk about the next question. This is also on one of the previous year question. So the correct order of the Hammet reaction constant for the deprotonation of the following carboxylic acid. So now you can see deprotonation, so it will form this type of carboxylate intermediate. Now the effect of substituent is dependent on the distance. As you know, if someone is far from you, that person can't pull you as much as someone who is closer to you. So this effect is dependent on the distance. Now this benzoic, so the reaction is totally based on the stability of this anion. Stability of this anion moiety. So suppose if there is any reaction, where this effect is lower because of the distance, then the rho value will be lower. Now say this is 1 carbon away and this is 2 carbon away. So obviously the effect will be higher in case of A. So A will be greater. Then it is 1 carbon away, so B, then C. So the correct answer will be this one. Whenever, so this Hammet equation or the Hammet principle is dependent on the distance. As the distance increases, the effect decreases. If the distance increases, the effect decreases. Okay, so let's go to our last question, which is the true statement regarding Hammet reaction constant for the following transformation. So they have given this one, this ester hydrolysis reaction, and this one. So rho, as I have discussed, whenever there is a huge distance, the effect will be lower, and as it is a ester hydrolysis and the product is a negatively charged, so it will be so the rho will be negatively charged, so the rho value will be obviously positive in both of the case, because our product is negatively charged, just similar to the benzoic acid. The rho value will be positive, so the rho value will be positive, so rho value will be positive, and in case of A, the rho value will be greater than that of B. So option C will be the correct answer, because here the effect will be less. Here the effect will be less because of this distance. So the correct option will be option 3. Understood? Okay. So these are for you. Just try it. What will happen? What will be the rho value? So this is simple case. This is also like it will be less than that of the normal because of distance. This is not. This is simple. The rho value will be less. I am giving this one. Try this one by yourself. and try to get an idea that what will be our rho value. Rho value will be positive or negative. Rho value will be positive or negative. Okay. I will get back to you in the next class. So thank you everyone. Have a nice day. Try to check this one and try by yourself. Thank you.